Okay. So tests should be done probably by tomorrow. Get close. I just started today, just last hour, and I got the first page done out of all 4 classes. I'll get the second page done hopefully today, if not tomorrow. And yes, that I did grow up on a dairy farm. Yes, I did milk cows. Yes, I listened to country music, but we did not weigh the milk. That was all made up. Yes, my dad listened to talk radio. Just talk. Now I listen to talk because I'm old. But I listen to sports talk. So this worked out pretty well first hour. I'll do it again for you guys. If you are, I didn't do any examples. I basically explained what we're doing today. If you feel like you need examples, they're all over here. They're hidden. You'll see at some point. I think you have. I know you have access to this because I just shared the same thing. See how these are all blacked out? When I hit next, I skip all those. So those are like examples. But first hour seemed to think that was okay. They actually finished the homework in class rather than me go over like 4 or 5 different examples. So we're going to go with that today. If you feel like you need them, there they are. I'm going to talk about everything that you need to, but it worked out well. So I think that works out better for you guys to basically explain what these things are. Okay. This is our last chapter. So there's 3 sections in this chapter. Okay. It's called a chi-squared. It's not chi, it's chi. Chi-squared. There's 3 different chi-squared tests. We're going to talk about one of them today. We'll talk about the other 2 on Wednesday. And then that's 12.2. And then 12.3 is linear regression. Which I know has been a long time since we've talked anything about linear regression. We'll talk more about that than we actually will the testing of it. But again, this is just kind of see where we're all at. We will take the test for you guys. It was this A, so we'll take it that Friday before spring break. We'll come back from spring break and we're going to start reviewing. So it works out pretty well this year. So you got to relax that whole spring break. We don't have to think anything about stats, do anything. We're just going to go back and start reviewing for the test. Okay? You got something there? What grades do we have during that? I change that up every year. A lot of times it's mostly in-class stuff. Most time I do everything in class. Very seldom do I give you guys homework. Again, I've hammered you guys all year. Pretty much what we're going to do is we're going to do in class. Very seldom do I give you guys something for homework. If you're missing class time, you're probably going to miss those points. But pretty much it's kind of do on your own. Sometimes I don't know. 16 years, I've probably done it 16 different ways. Whatever I did last year is what I probably need to do because that was the highest ever average. Everybody else okay? Good? Chi-squared. Here we go. So let's kind of wrap your head around this. One thing about chi-squared is there's no intervals. It's all tests. So we're done with intervals. So if it's means, intervals, or proportion intervals, it has nothing to do with chi-squared, okay? Let's go back to chapters, golly, what was that, 8 and 9, where we did all proportions, is all categorical data. So 8 was, I think, the confidence intervals, 9 was the test. And then we did means, confidence intervals, and tests. Categorical data is categorical. You either are in that category or you're not in that category, right? You either drove to school or you didn't drive to school. It's either a pine tree or not a pine tree. Whatever it might be. You either have an A or you don't have an A. It was categorical, but that's how it was. It was basically yes or no or success or failure type deal, which why we can also do binomials with those, but all that stuff's easier than a binomial, which is why we only talk about binomials for a little bit. And then it was means, numerical data, okay? Numerical data. So proportions, right? That was chapters 8 and 9. One sample is either 2 samples. It was a test or an interval, and it came from categorical data. It was either yes or no, good, bad, whatever, right? Means was chapters 10 and 11. It's either one sample or two samples. It was either a test or an interval, and it dealt with numerical data. Chi-squared goes back to categories, but it's not just yes or no. It's more categories than two. It's more categories than two. Your grade in class, A, B, C, D. Thank you. Super Sid. It could be the color of the car. So rather than be a white car, like 26% of all cars are white. Well, that was chapters 8 and chapters 9. Now we're going to say 26 are white and 23 are blue and whatever, right? Now we're going to fit into any one of those. Yeah, whatever it is. I didn't even read it, obviously. Okay, so we're going to have more than two categories. So when that happens, we're talking about chi-squared. This is a Greek letter. Oh, darn it. I didn't turn that on. Sorry, let me put my little writer on. It is a Greek letter. It's a lowercase chi. So, but it just kind of looks like an X. Oh, let's turn the pen on. How about that? Chi squared. And it's just squared like the exponent 2. Okay, chi squared. So just a little thin, fancy X. Okay, you'll see it italicized or something. Returns back to categories, except instead of 2 categories, we have more than 2. We have more than 2. Okay, so let's first talk about the chi-squared distribution. This is important to know. This is different, right? We've talked about normal distributions. We talked about T distributions. Now we're going to talk about chi-squared distributions. Chi-squared distributions only take on non-negative values. They will not be negative. They are all positive. Z's and T's, they had 0 in the middle and positives to the right and negatives to the left. Chi-squared are only positive. They're only positive. Okay? So they're only positive values. Chi-squareds are skewed to the right. They're skewed to the right. So they're different than Z's and T's because Z's and T's were somewhat normally shaped, or they're high in the middle, low in the ends. So they're skewed to the right. They are distinguished by DFs. They do have DFs. So we'll talk about them throughout this lesson, but they do have DFs. And as DF increases, that curve starts shifting a little bit, becomes less skewed. They're all skewed. It just becomes less skewed. Okay, and you'll see the example here in just on my next slide of me showing you 4 different chi-squared curves. 4 different chi-squared curves, but they're only non-negative. That's a big deal. We're not used to seeing non-negative. I mean, we're used to seeing non-negatives, but we're also used to seeing negatives. These are only non-negatives. They're all skewed to the right. We're not used to seeing that. We're used to seeing symmetrical. T's are, so light T's, DF change, or DF changes the curve. DF changes the curve. So they're not constant. And as it increases, it just becomes less skewed. Here's 4 of them. This is a DF of 1, which you will never see, because a DF of 1 is nothing more than proportions. And really, this is like rest of the normal curve. That blue is rest of the normal curve. You won't ever see that one. This red one has a DF of 4. It actually starts at 0. It starts at 0, goes up, and then curves down. Okay, you can see the area and the tails. This one has a DF of 8. Okay, so you can see it's less skewed. In fact, it'd be kind of hard to argue that that wasn't somewhat normal. However, it's not centered at 0. Okay, I don't think you'll see much higher than DF of 8. I don't think 8's pretty high. 8's pretty high. Good enough, okay? Pencils are still. The p-value is always going to be the area to the right. So whatever that chi-squared value is, it's always the area to the right. It's always the area to the right. Chi-squared, area to the right. Hey, we've talked about normal CDF. We've talked about TCDF. Well, now we got to talk about chi-squared CDF. All 3 of those find the p-value. All three of those find the p-value. This has a lower bound, upper bound. This has a lower bound, upper bound DF. And I was surprised that this actually has a lower bound, upper bound. Why do I say I'm surprised? Because the lower bound's always the chi-squared value. It's always the chi-squared value, and the upper bound's always 9999999. And then the DF. Okay, so that finds the p-value if you know the critical value. This one's z's, this one, of course, is t's, and then this one, of course, is chi-squareds. So we have t distributions, we have z distributions, we have chi-squared distributions. Okay, it's our last distribution. Yay. Here's the chi-squared with a DF of 4. There's the chi-value, chi-squared value, 8.18. So this would be the p-value. So you got to know 3 things. Well, you have 2 things, I guess. You got to know the DF, and you got to know the chi-squared value. If you know the chi-squared value and you know the DF, you can find the p-value. And the p-value is just like what we've always done. That's 0.08, so we probably failed to reject. Failed to reject. There's not enough evidence to say that, and we'll talk about the ho and the ha in just a second. So all that's still in play. You still make errors. Okay. You either will use the table, which most of you don't use, or you'll use your calculator to find that p-value. Okay. All right. Give you a little heads up. I kind of have already. There's 3 kinds of chi-squared tests. The first one's called goodness of fit. Goodness of fit. We will abbreviate that as GOF. It's okay to call it GOF test. Everybody knows what you're talking about when you say GOF, goodness of fit. And guys, this is univariate. Univariate. Color of car, 1 variable. Color of car, 1 variable. Your grade, A, B, C, not number-wise. A, B, C, or D is categorical. Okay? It's 1 variable. 1 variable. Kind of tree. Kind of tree. Color of hair. It's 1 variable. 1 variable. Okay? GOF. GOF. Just to somewhat lead you into it, on Wednesday, we're going to talk about independence, and we're going to talk about homogeneity. Okay? Homogeneity. Or homogeneity. I don't know. I think it's homogeneity. But I used to call it homogeneity. Those are what we're going to talk about on Wednesday. And this is the hardest thing about this chapter, guys, is to decide which one of these it is. Is it a GOF? Is it independence? Is it homogeneity? Now, you don't have to worry about that till Wednesday. You don't have to worry about that till Wednesday, because they're all going to be GOFs today. But this is univariate data. Univariate data. Independence, it'll be bivariate data. Bivariate data. Gender and what toy they like. Gender and what toy they like. Gender and what color of car you drive. And I don't think there's any association whatsoever. But two variables. And in homogeneity, there's going to be 2 samples. 2 samples, which sometimes gets a little confused with that. And you'll see that. But anyway, don't get too much wrapped up into this yet. This is what we're concerned with, goodness of fit today. Goodness of fit today. I'll probably have to do some examples Wednesday. Goodness of fit. Or pencils, anybody going? Still good? I know you can't see anything from over there. Okay, conditions. Got to have conditions. Bet you already know them. Random. Got to have a random sample, or a sample that's representative of the population, or whatever we got to do. We got to have a random, right? We've done that all year since January. Everything's been random. We still have to have the 10%. My sample needs to be less than 10%. Guys, I just graded some of your tests, and this, I don't know if it's you or whatever. Some people are a little confused with this. I'm seeing greater than 10%. I'm seeing that you want your sample size to be less than 10% of the population. Some of you guys are Some. It's a very, very small amount. But some are a little confused with that 10%. They're trying to mix that with large counts or that are, okay? And then large counts. Oh, there it is. So you kind of see how I did it, right? N is 10% of big N. Big N is the population. And then large counts. Large counts. Now this one, just like all the others, is a little different. It's a little different. So this is what this one is. All expected counts. All expected counts are at least 5. We need those expected counts to be greater than or equal to 5. So write that, and then we're just going to talk for just a little bit. And again, this talking bypasses some of my examples. So this is for GOF. Goodness of fit. We're going to have 2 different counts. We're going to have 2 different counts. We're going to have the expected counts. What do we expect to show up? If grades are evenly distributed, then we expect, let's say that there's what, A, B, C, D, F. If grades are evenly distributed and there's 10 of them, or sorry, 50 of them, I gave you the answer, right? If there's 50 grades and they're evenly distributed, we expect there to be 10 in each category. That's what we expect. We're also going to have observed counts. Well, that's what we actually see. That's what we see. So I'll go to the grade book and I'll count how many A's and count how many B's and count how many C's and count how many D's and count how many F's there are. And that's what I actually do see. Those are my observed counts. We're going to see how well they fit. Goodness of fit. How good does it fit? That's really bad English, but that's goodness of fit. How good does what I observe fit with what I expect? So we need those expected counts to be greater than 5. Be careful, because a lot of students will show the observed counts on that. I need the expected counts to be greater than 5. Y'all okay? Pencils, pencil, pencil, pencils. Don't write that. I skipped that one last time. It worked well. This is just N times P, showing me how to find expected counts. Well, if P is, I don't know, 0.2, and there's 40 of them, then I would expect 0.2 times 40. Everybody did okay with that without showing. Make sure it's the expected counts and not the observed. Okay, this is an AP exam tip. So the guys that grade AP tests wrote this book, and they see these mistakes a lot. And so when they see these mistakes a lot, they just say, hey, this is a tip. Make sure it's not the observed counts. Make sure it's the expected counts. Make sure it's the expected counts, not the observed. And make sure you prove it. Okay, the hypotheses. It's hypotheses. So again, we're going to talk a little bit about this. We know from some chapters it was P equals. We know some other chapters it was mu equals. In this particular chapter, it's going to be more of words. Bless you. Now, I could write P of A equals what? 20%, 20, 40, 60, whatever's left. 20, 40, 60, 80, yeah, 100. So A would be 20%, P of B would be 20%. Y'all okay? I could write that down if I wanted to, but I don't want to write down all those. So the whole is pretty much going to be in words. What we do is we expect, or we, let's see, the expected counts, how about this, will equal the observed counts. We're going to assume they're going to equal. We're going to assume they're going to be the same. Well, that's all we've done with all of our hos. We always show equals for hos. We always show equal for hos. So that's what we're going to try to do. And I'm going to get this question, guys. I get this from whatever their question says. This has to be in context. That has to be in context. So the grades will be evenly distributed. If you want to say that, that's okay. The grades will be evenly distributed. Or the grades will equal what we, the observed grades will equal what we expect. I think I said that, I kind of said that backwards probably. Because you're going to have your observed, we want them to equal the expected. And then the high is that they won't. Not equal. Wait a second, isn't not equal like a two-sided test? Not for chi-squared. Not for chi-squared. We know that two of them, I mean, they could be a little different, right? This one may not be this equal to this one may not be equal to this one, and this one may not be equal to this one, but this one might be one off, and this one might be one the other way off, and it's still going to be okay. They're still going to be okay. They say what they're equal. If I just want to compare two, then I'm going to do chapter 8 and chapter 9. Chapter 9. I'm going to do 8. 8 was confidence interval. I'm going to get whatever that is from the question. From the question. From the question. Whatever their question asks. I'm going to go to that question, and then I'm going to assume they're going to be equal. I'm going to assume that one of them I use always confuses some students. Some type of animal, insect, have certain type of wings. I don't know. Whatever. And it follows a 4 to 3 to 3 to 1 ratio. In other words, 4, 5, 6, 7, 8, 9, 10. 40% will be in this one, 30% will be in this one, 30% will be in this one, and 10% will be in this one. So I would expect the population to follow the 4 to 3 to 3 to 1 ratio. Make sure it's always the population, make sure it's the population, make sure it's not my sample. A lot of students will mess up there. They'll talk about the samples. And then I expect it not to follow the 4 to 3 to 3 to 1 ratio. But anyway, I always get these from the question. It will make more sense to you as you start working these, I think. Is that? Nope. I mean, you have to write, and leave write all of them out. Formula for this. Formula for this. It's written on your formula sheet. It's different than all the other ones we talked about. Chi-squared equals. We're going to take this big old summation thing, right? That means we're going to add a bunch of things up. And we're going to take our observed counts and we're going to subtract our expected counts. And then we're going to square that. Y'all can see where that gets a positive, right? That gets to be a positive, always. So whatever the difference is with what I observe and what I expect, I'm going to divide that by what I expect, which we know that number is going to be bigger than 5. Because if it's not, I don't fit my condition. So that's the value that I get. I'm going to add it to each one of those. So if there's 4 categories, I'm going to have 4 of these numbers I'm going to add up. So if I observe, so here I have observed and here I have expected, right? You kind of picture this. I observe that there's 4 white cars. I expect there's going to be 8 white cars. I observe there's going to be 3 blue cars and I expect them to be 5 blue cars. Probably not doing a very good job. Let's expect more. I observed 8, I don't know, dark cars, and I expect 5 dark cars. This minus this is 4. Square it, 16 divided by 4. Plus this minus this squared divided by. I mean, we don't have to do it all. The calculator's going to do it all. The calculator's going to do everything. You just kind of need to see the formula and how it works. Observed minus expected squared over expected. Good enough? Yep, hit me.
What's the, like, if you don't want to write the formula, what's the word?
So it's going to be a chi-squared goodness of fit test. Chi-squared goodness of fit test. The method or the formula, right? This one, I'm almost going to recommend the formula before the method, especially after tomorrow, or after Wednesday. Yep.
For like the formula, how would we like?
I'll show you. I'm getting ready to show you. Yep. I kind of mentioned all this stuff. It's univariate data, one variable. This, again, it's all going to be that way today, so it's not going to be that big of a deal. It's when we add Wednesday. You want to see how well we observe fits with what we expect. How well we observe fits with what we expect. How good does it fit? Goodness of fit. How good does it fit? How well does it fit? The observed counts will equal what we expect. I already talked about this. They will not equal to what we expect. We already talked about that. Be sure to write that in the context of the problem. You'll get that within the deal. I got a worksheet this time. I've already done this worksheet, so you'll get this stuff. This just really start making sense to you, I think. Oh, DF. This is big. Number of categories minus 1. Number of categories minus 1. Grades, A, B, C, D, F. DF is 4. Color of cars, I don't know. If there's 9 colors of cars, DF is 8. Y'all can see what I told y'all, DF of 8's be pretty high. There's not that many categories normally. There's not a whole lot of categories normally. Number of categories minus 1, which is, I mean, we got the minus 1 down a little bit. It's just, it's not in. Now, we'll get some students that will mess up, right? If I have a sample size, this sample size of 20, some might say the DF is 19. No, number of categories minus 1. Number of categories minus 1. How are you going to do this in your calculator? This is good to know. This is what we want to do. Stat edit. Stat edit, L1, L2. We're getting pretty good at that. Okay? You put your observed in one of them. Put your observed in one of them, and you put your expected in another one. If they're not equal, you're going to get an error. When you do this in your calculator, if they're not the same number, not equal, not 12, 12, if it's not 4 and 4, because if it's 4 and 5, you're going to get an error because you can't do 0 minus it. Okay? So put your observed in one of them and your expected in another. Observed in one and expected in another. Doesn't matter which ones. I like to keep observed in L1 and your expected in L2 because that's kind of like the default. But you can put them wherever you want. Put them wherever you want. If you don't have 1, 2, 3, 4, 5, 6, always do stat setup editor. Stat setup editor will do a 1, 2, 3, 4, 5, 6. And if you want to clear them all, you can do stat plus, second plus. Clear all this. That does it all at one time. Okay, so L1, L2, okay? And then you go stat test. Anybody have the old 83? I thought somebody in here had an old 83. It doesn't have a GOF test. The old 83 doesn't have a GOF test. The 84s do, the Inspires do. But the old 83s, the old black 83s, there's not very many of those running around. They don't have a GOF test. But it's stat test. Yep.
Wait, so the chi-square distribution, the chi-square
Chi-square.
Test statistic, are they the same thing?
Yes. Well, the distribution is the shape of it, and the test statistic is that value. Okay. You have a t distribution and a t critical value, right? So, and this, when you go to chi-square GOF, now make sure there's 2 chi-square tests on your calculator. Make sure it says the GOF one. Okay, make sure it says the GOF one. You're observed, it'll ask you for those, it'll ask you for your expected. So that's just wherever you put them. Where'd you put them? Did you put them in L1 and L2? Put them in L1 and L2. If you put them in L3 and L4, go to your observed and hit second 3. Second 3 is your second, that's L3. Second 4 is L4. Second 5 is L5. Second 6, L6. And then you got to tell it DF. It's not smart enough to know that that's 1, 2, 3, 4. It's not smart enough to know that's 3. You got to tell it 3. And then you just hit calculate. And when you hit calculate, it's going to give you the chi-squared value. It's going to give you the p value. It's going to give you DF again. Okay? And then notice what else it gives you. It says CNTRB. Okay? Those are the contributions. That 7.2 is 32 minus 20 squared over 20. That 0 is 20 minus 20 squared over 20. 16 minus 20 squared over 20. 12 minus 20 over 20 squared. Okay? If you add up all of those values, you will get 11.2. You will get 11.2. Y'all okay? Most of the time, you don't need those. Most time you don't need those, but it's there. There is a question on homework a lot of times, and I have seen it on one of the AP practices, but not very many. Which one of the values has the biggest impact on that chi-squared? First one. First one, because it's 7.2. That has the biggest impact because it has the biggest difference. 32 to 20 is bigger than all the others. It's not because of 32 to 20, it's because of 32 to 20 squared over 20 is the biggest. But, y'all okay? So those are there. CNTRB, contributions. That's what that says. I explained all that. You can use your calculator. You guys know this for your test, for your mechanics. There's a risk involved, as you guys know. The problem with using your calculator for everything is if you mistype one of those numbers, you're going to get something wrong. And we as graders don't know what you did wrong. So here's what they're going to talk about. We recommend writing out the first few terms of the chi-squared calculations. Write down 32 minus 20 squared over 20 plus 20 minus 20 squared over 20. And then they say, that's enough, plus ... You don't need to write them all down. You don't need to write them down, all down. But by doing that, if you mistype something, they understand you know what you're doing. You just mistype something, you'll still get full marks. But if you just have a chi-squared value down there, they're probably not going to give you full marks. So that's their recommendation. This approach might help you earn partial credit if you enter the number incorrectly. Be sure to name the procedure, chi-squared test for GOF, and report the test statistic, chi-squared, the degrees of freedom, and the p-value. Report all those things, but you guys know that because that's what your calculator gives you. The calculator gives you those three things, so you're going to report those three things. You don't have to report the contributions if you don't want to. You can, it's not wrong. But you've got to report those other three. If the P is low, you still got to reject. If the P is not low, then you can fail to reject. We still don't accept. We still don't do anything wrong. We still can make a type 1 error or a type 2 error. I'm done. Let me, real quick. I don't feel right by being done that quick. Okay, real quick. Look at this example, and I'm going to do it for you. We're not going to do the whole thing. I just want you to look at this example. Carrie made a 6-sided die in her ceramics class. Okay? Rolled it 90 times to see if each was likely to show up. This die will equally show up on all 6 sides. Or this die will have equal representation for all 6 sides. We're going to say something like that for the hoe. And in the it will not. At least one side will not. Something like that. You don't have to say they all, at least one. Y'all okay with the hoe and the right? Now, if I rolled it 90 times, I would take 90 and divide it by 6, and that's how many I expect to show up each time, because it should be equally distributed. And so those are my expected counts. They should all be greater than 5. Okay with that. So you got a random selection of rolls. 90 rolls is less than 10% of infinity rolls. And each expected count, all expected counts are greater than 5. And at some point, here's the outcome. These are the observed counts. So I don't say all those are greater than 5 because those are observed. So I'm going to put those bad boys in L1, and I'm going to take 90 and divide it by 6, and I don't know what that number is. 15? There it is, 15. So it should be all expected counts are 15, which are greater than 5. That's all I got to say. All expected counts are equal to 15, which is greater than 5. You're good there. Okay? Here's what they said the hoe was. Where was that at? The sides of Carey's die are equally represented to show up. The sides of Carey's die are not equally represented to show up. Okay with that? Not too bad, right? And then they're going to do everything in their calculator. Oh, this is a different one. The birthdays will equally likely show up. I don't expect them to be a heavy-sided birthdays. They'll tell you inside the problem if they don't expect it equally likely. I think I do one of those. Here's M&Ms, I think. Let me do it. Here's the M&Ms. See where I wrote all this stuff. Here it is. No, that's the sample. Here, this is what M&M says their distribution of candies is. It's not equally represented. So however many candies I have, I take 12.5% of those, and that's how many should be brown. That's how many I expect to be brown. So those are your these are not your expected counts. Don't get confused now. Those percentages are not your expected counts. Those are expected percentages. So you got to know how many M&Ms we have to know expected counts. If there's 100 of them, then I expect 12 of them to be brown, I expect 12 of them to be red, and I expect 12 to be yellow, and I expect 12 to be green, and I expect 25 to be orange, and I expect 25 to be blue. And these are all halves. Yes, 12.5. Expected counts can be decimals. Your observed counts cannot be decimals. You can observe a decimal. That will give you an error on a calculator too. Okay, I'm done. You should be able to. Just to make sure. Come on. You should be able to state the appropriate hypotheses and compute the expected counts. You should be able to state and check the randomness with 10% and the large counts condition. You should be able to calculate the degrees of freedom. Don't use your calculator. And the p-value, use your calculator. For the chi-square test, perform the chi-square test for goodness of fit, and then conduct a follow-up analysis when the results of a chi-square test are significantly significant. Because the p-value is less than 0.05, I will reject the null. There is convincing evidence that these dates are not equally distributed. Whatever. The biggest question I had first hour was about how to use the table. And I just told them I don't use the table. I use the calculator.